In our last lecture, we had discussed the Doppler effect in light. As we had said, that Doppler effect in sound is well known. We visualize many times in our daily life. But in light, it requires slightly different treatment, and it's probably not so much apparently known. We also discussed a special Doppler effect, which we call as a transverse Doppler effect, which is normally, which does not have any classical analog and will not be seen in sound for that matter. These two aspects we discussed. Then we gave some flavor of some experiments in which Doppler effect is used, just to give an idea that the Doppler effect that we have talked has certain usefulness as far as certain part of physics is concerned. In fact, it's even in medical sciences the Doppler effect is used quite effectively. So I think Doppler effect is finding more and more uses. But what we did in last lecture, just to give some idea about the Doppler effect. Today we would like to go to a slightly different concept. Basically, it's for problem solving. We define what we call as a center of mass frame of reference. Normally, in classical mechanics, when we are not dealing with relativity, the center of mass is always described in a fashion such that we have a standard definition of center of mass, how to find it out. And if we change our frame of reference to that center of mass of a system of particles, then we call that particular frame of reference as center of mass frame of reference. The advantage of dealing with center of mass frame of reference is that if there is no external force to the system, center of mass becomes an automatic inertial frame of reference. Because if there is no external force to a system of particles, the center of mass must be at rest or must be moving with constant velocity as seen from any other inertial frame of reference. So if we move ourselves to the center of mass, automatically we are landing up ourselves into an inertial frame of reference. Now we slightly modify this particular definition as far as relativity is concerned, and we say that center of mass frame of reference is that frame of reference in which the sum of the momenta of all the particles is 0. This center of mass frame of reference is occasionally referred as C frame. So what we have said, that center of mass frame is a frame in which the sum of momenta of a system of particles is 0. Normally, as we have always said, that there is a set of particles which we consider as a system in which we are interested in. See, there could be forces in between the particles. It means a force being applied by one particle on any other particle, that we call as the internal force. And if a force is applied by a particle which is not a part of the system, that's what we call as an external force. So I repeat that if we find that sum of the moment, if we go to a frame of reference in which the sum of the momenta of all the particles of the system is 0, that's what we call as C frame or center of mass frame. Similarly, we can define, or we generally call, a L frame as the laboratory frame of reference. This frame of reference is a frame in which you have described your problem, or you have described your experiment, or in which you may perform the experiment. This frame of reference could be a C frame, could be a center of mass frame of reference, or could be any other inertial frame of reference. So I may describe in a problem, my problem, in a frame of reference which does not happen to be a center of mass frame of reference, or I could choose to describe the problem only in a center of mass frame of reference. So laboratory frame of reference is a generic frame of reference in which we have described my problem or my experiment. Now, why we talk specifically of C frame, especially in relativity, we will see that many problems become very simple if we work it out in the C frame. Though the problem may not have been given to you in C frame, it might have been given in some other frame, but still if you transform the problem into C frame, the problem turns out to be simpler. So in today's lecture, we will be essentially discussing some problems in which we will find the use of C frame to be convenient frame and probably an easy frame. So this is what I have written in STR, which I mean special theory of relativity. Problems can be simplified when transformed to C frame. I would also like to mention that when we actually perform many HEP is stands for high energy physics. If we perform experiment like collision experiments or scattering experiments in high energy physics, many times we prefer to design this experiment in C frame of reference, in center mass frame of reference, so that overall there is the energy which is saved. We will be seeing little later that energy turns out to be smaller in the C frame of reference, basically because you do not have to spend energy to accelerate the center of mass frame of reference. It effectively means that if you have one particular particle and you want to design an experiment in which another particle comes and collides it, okay, in that case this frame of reference is not a center mass frame of reference because the net momentum is not 0. So, you would rather like to have an experiment in which both the particles come together and collide such that the center of mass, so that it becomes in a center of mass frame of reference, or the net initial momentum is 0. So, let us come to one particular problem which is actually a simple problem, but this illustrates the fact that how it can become simple if it is solved in C frame, and it is rather difficult to solve in L frame, even though the problem appears to be fairly simple. Let us look at the problem. There is a particle of rest mass capital M naught, which has a total energy of 3 m naught c square. Now, we must be clear that when we are talking of total relativistic energy, it means it includes the rest mass energy. So, the total energy, which means kinetic energy plus rest mass energy, is 3 m naught c square. This particular particle decays into two identical particles. So, this particular particle goes away and eventually decays into two particles. Each one of them have a rest mass of m naught. So, they are identical particles, whatever might be the particles. This may not be a realistic sort of experiment, it is just for sort of understanding of our problem. So, it decays into two masses, two particles, which both of which have a rest mass of m naught. Now, I have to find out what will be the velocity of these particular particles when they have decayed, given the fact that the decay product, it means both the particles move along the direction of the motion of the parent particle. Let me just read again. A particle of rest mass capital M naught and total energy 3 m naught c square decays into two identical particles of rest mass small m naught. Find the velocities of the two particles given that the decay products move along the direction of the motion of the parent particle. If I want to draw into a small simple picture, essentially it means that this is a particle which is of mass rest mass capital M naught. This is moving in a given frame and eventually decays into two particles, two small particles. Each one of them has a rest mass m naught. Obviously, because it has to conserve energy and conserve momentum, therefore, these particular particles will also be moving. What has been told that both these particles move in the same direction as this particular particle. So, it means they also move in this direction or opposite direction, but the total motion is confined only to one dimension, which we can call, for example, x direction. It does not matter what direction, but everything, the problem is just a single dimension problem, a one dimensional problem in which everything has been described. Now, in a traditional classical mechanics problem, where we have to conserve energy and momentum, this problem would have been absolutely simple. But we will see that if we try to work out this problem in this particular fashion, you will see that there are certain complications and it is not easy to work out this particular problem until we go to a different frame of reference, which is the center of mass frame of reference. Let us look at this particular problem. First, let us attempt to solve it only in the L frame, the laboratory frame, the way it has been described. We will discuss what are the difficulties which comes across. So, as we said, the idea is that we have to apply conservation of energy and conservation of momentum in this particular frame. Energy has been given because there is only one particular particle initially. So, energy has been given as 3 m naught c square. So, I have to find out this energy and we have to find out correspondingly what is the momentum of this particular particle. Once we find out the momentum, I know the initial energy, I know the initial momentum. It decays into two particles. We have to write initial energy is equal to the sum of the energy of the resultant particles. Similarly, initial momentum vector is equal to the initial, the final momentum. That is what we have to do. So, let us first find out the initial momentum. We have been given that E is equal to 3 m naught c square, and if you remember what we have said, that the energy is given by gamma m naught c square, where m naught is the rest mass of any particular particle. And in this particular case, because the energy has been given as 3 m naught c square, it is quite clear that gamma is equal to 3. Only thing, because this has been described in laboratory frame of reference, so let us write a subscript L to make it clear that this gamma that we are talking, or the velocity that I will be talking, on which this particular gamma depends, is actually the velocity in the L frame or in the laboratory frame. Now, once we have this particular gamma L, I can always find out what is the velocity of this particular particle, and once I find out the velocity of the particle, I can always find out the momentum of the particle. Of course, I can also use direct energy momentum relationship, that also I will use, just to show that we get the same result. Okay, let us first try to find out the velocity value using this gamma L. If you remember, the value of gamma, the expression for gamma is given as 1 upon under root 1 minus v square by c square. Sometimes we have used v, sometimes we have used u, but I think it should be clear by now when we use v, when we use u. Now, I want to solve it for v upon c. I want to know, if I want to have, if I know the value of gamma, I want to find out the value of v by c. So, let me square it and take inverse of it. If I square and take inverse of it, I will get 1 upon gamma square. Square it, so this under root goes away. Take inverse, so 1 minus v square upon c square comes on the numerator. So, this becomes 1 minus v square by c square. So, I can solve this particular equation. So, this becomes v square by c square is equal to 1 minus 1 by gamma square, which means v by c square is what we call as beta square in our notation. So, I can write this as beta square as, I am sorry, there is no, let me do it here. Beta square is equal to gamma square minus 1 upon gamma square. So, this is the expression which I have written in this particular transparency, that beta is equal to under root gamma square minus 1 upon gamma square. So, this expression gives me the value of beta, which is v by c, using the value of gamma that we find out. In the present case, gamma is 3. So, I substitute it here. This becomes 3 square minus 1. So, this becomes under root 8 divided by gamma square, which is 9. This 9 can be taken out of the under root sign. So, this becomes under root 8 by 3. So, this p, I am sorry, this beta is under root 8 by 3, which is v by c. Now, once I know the speed, I can always find out what will be the momentum of the particle, and the momentum of the particle, as we know, is given by the momentum is equal to gamma m naught v. We know gamma is equal to 3, m naught is m naught, and v is under root 8 by 3 c, we have just now found out. So, I have substituted this in this particular expression. So, P L, L is again, because I am describing this in the laboratory frame, is equal to 3 multiplied by m naught multiplied by root 8 by 3 c, which gives me root 8 m naught c. Of course, as I said, I could have found out this particular expression also by using directly the energy momentum relationship, which is E square is equal to P square c square plus m naught square c to the power 4. This is a very commonly used relationship. So, from this particular thing, I have to evaluate momentum. I know the energy. So, P square c square will turn out to be equal to E square minus, I take this on the other side, minus m naught square c to the power 4. E being 3 m naught c square, E square will become 9 m naught square c to the power 4. So, I substitute it here. I have to subtract this expression minus m naught square c to the power 4. So, this becomes 8 m naught square c to the power 4. C square I will cancel out, and P I will get under root m naught c. So, what we have done so far, I know the energy, the initial energy of the system, which happens to be just one particular particle, which now eventually decays into two particles. So, this particular particle has a total energy of 3 m naught c square, and it has a total momentum of under root 8 m naught c. So, once this particular particle decays into two particles, the total energy must remain same. Similarly, the total momentum must remain same, because this is purely a one-dimensional problem. So, I have not taken the x-axis and y-axis, I was just describing, I have not described it in the vector form. All I need that this particular value of momentum must be conserved. So, I will be able to write the following equations which I have written in the next transparency. Once we have found out what is the energy and the momentum of the original particle, what we have to do is to write the energy and momentum conservation equations. We have seen, in fact, it has been given in the problem that the initial energy is equal to 3 m naught c square. There is only one particular particle, so there is only one particular particle system. Once there are two particles which have resulted out of the decay of this particular particle, if E1L and E2L are their energies, then 3 m naught c square must be equal to E1L plus E2L. Now, corresponding to 3 m naught c square, I have seen that the value of the momentum is under root 8 m naught c. Remember, this is the original particle, so I have used capital M naught here. This must be equal to the sum of the momenta of the two particles. We have been told that the particles move along the same direction as the original direction. So, I can write just in a scalar form. I do not have to use vector form, because as we have said, this is purely a one-dimensional problem. So, this must be equal to P1L plus P2L, where P1L is the momentum of the first particle, P2L is the momentum of the second particle. As I have said, E1L is the energy of the first particle, E2L is the energy of the second particle. In a traditional classical mechanics, this would have been a very, very simple trivial problem to solve. All you have to do is to express this energy into momentum in the form of momentum, or this momentum into the form of energy, and just solve these equations. You have two unknowns and two equations to solve it. This would have been very simple, mainly because in traditional classical mechanics, in which there is no relativity, the relationship between E and P are fairly simple. Of course, in that case, rest mass, what we try to do is to conserve the kinetic energy. Okay, let's not bother about that thing as of now. Now, in this particular case, what we will find out that the energy and momentum relationships are a little more involved, which has been written in the next transparency. So, the energy of the first particle is related to the momentum of the first particle by this particular expression, E1L square is equal to P1L square c square plus m naught square c to the power 4. Remember, I am using small m naught because the energy and momentum of the particle that I am going to relate has a rest mass of small m naught. This is not the original particle. The original particle has now decayed. The resultant particle which I have got, which has a rest mass of m naught, and fortunately in this particular problem, the two particles have the same rest mass m naught. That is what has been given. So, I am using small m naught here in both these expressions. Exactly similar equation I write for as a relationship between energy and momentum of the second particle. E2L square is equal to P2L square c square plus m naught square c to the power 4. Remind that this L has been written just to make sure that I am talking of laboratory frame of reference. As we will see, that it is not very easy to solve these equations, because if I try to express this particular equation in that particular form, let's try to express energy in terms of the momentum, then I have to take under root of this particular expression to find out what is E1L. So, I must write E1L is equal to under root of P1L square c square plus m naught square c to the power 4. Similarly, for E2L, I have to write under root P2L square c square plus m naught square c to the power 4. When I write in the conservation of energy expression, I have to write 3 m naught c square is equal to this plus this. So, this becomes this under root plus this under root. If we can solve this equation, of course, we will get energy and momentum. In fact, we will get P1L and P2L. Taking the other equation also into consideration, writing P1L also in terms of the initial momentum, I will be able to solve it. But as you can see, because of the presence of these square roots, etc., these are not very straightforward equations to solve. On the other hand, this equation becomes fairly, this problem becomes fairly simple if I go to the center of mass of frame of reference. So now let us attempt to solve this particular problem in center of mass frame of reference. Of course, here the problem is fairly simple because there is only originally one particle. So if I have to find out what is the velocity of the center of mass, it is going to be the velocity of the particle, the initial particle that I am talking about. So I go to a frame of reference in which the initial particle is at rest, and because in this frame the particle is at rest, the momentum is 0, there is only one particle, so that automatically becomes the C frame or the center of mass frame of reference. So let us describe, let us go to a frame of reference in which the original incident particle or undecayed particle, not the incident but undecayed particle was at rest. So this is what I have said. Let us go to C frame. As there is only one single particle, we shall have the following conditions. I know very clearly, because if I have gone to the frame of reference of that particle itself, the particle is not moving in that frame. Therefore, its total energy has to be only the rest mass energy. There cannot be any other energy. Therefore, the total energy in C frame will have to be just m naught c square. And of course, if the speed of the particle is 0, then momentum is also 0. So therefore, in the C frame, the initial value of momentum is 0, which has to be if it is to be called a C frame, and the total initial energy is just capital M naught c square. Now, let us try to see if I have to conserve energy and momentum in this particular frame of reference. Remember, because the rest mass of the two particles that I am getting as a result of decay happen to be same, the only way these particular particles can decay is when they move back to back. It means one particle goes in this particular fashion, another particle goes in this fashion, opposite fashion. That is the only way that they can conserve and make momentum 0, because remember, initially the momentum is 0, so the final momentum also has to be 0. If the both particles move in the same direction, there cannot be momentum, cannot be 0. We have been told that they move only in one line, so there is only possibility is that one goes in this particular fashion, another goes in this particular fashion. And because their rest masses happen to be same, therefore, their energy has to be equally shared. Because in order to conserve momentum, both must have same momentum obviously, and energy and momentum relationship depends on their rest masses. Their rest masses being same enforces that their energies are also same. Let me just explain this particular part a little bit more. So we have E square is equal to P square C square plus m naught square C to the power 4. If for first particle P is same as the second particle, m naught is same as the second particle, then E of that particle also has to be same as the second particle. Therefore, the two particles in the center of mass frame of reference must have the same energy as well as the same momentum. Same momentum because the initial momentum was 0, so final momentum also has to be 0, and energy have to be same because their rest masses also happen to be same. Therefore, we can see that the problem is extremely simple. It means each one of the particles must be having a energy of half m naught c square. So this is what I am written here, that m naught c square should be equal to 2. This is I can write as gamma c m naught c square. So this m naught c square, the total energies have to be equally shared, and this energy of each particle can always be written as we have just now said gamma m naught c square, and because this is center of mass frame of reference, so I am writing gamma c. So each particle must be having the same energy. So this 2 must be equal to the total initial energy in this frame, which is m naught c square. So this is what I have written, m naught c square is equal to 2 gamma c small m naught c square. It immediately gives me the value of gamma c, which is c square cancels here, m naught divided by 2 small m naught. Once we have found out the value of gamma c, I can immediately find out what will be the speeds of this particular particle in this particular frame of reference by using the expression which we have just now written earlier. So the two particles will move in opposite direction with the following speed. This expression is the same expression which we just now have worked out a little bit earlier. And if I substitute the value of gamma c which I have obtained, I will get that the speeds of the particle will be like this, will be given by this expression, one moving in plus direction, another moving in minus direction. You can call it x direction, one moving in plus x direction, another moving in minus x direction. So these are the two velocities. But what we have found out are the velocities in C frame of reference. If I have to find out in laboratory frame of reference, all I have to do is to do a simple velocity transformation. I have to know what is the velocity of the C frame, which by the way we have found it out earlier. Okay. Once we know the velocity of that particular frame, take care of proper signs and you can transform back and obtain the values of speeds or the velocities in laboratory frame of reference. So we transformed it to C frame, then brought it back to L frame. But remember, the problem is very simple now. We don't have to deal with all those under roots and trying to work out and trying to solve those equations. The problem is essentially very simple. So these I have written. These speeds have only to be transformed back to L frame, taking care of appropriate sign. The speed of C frame in L frame needed to apply this transformation. This was already found out earlier, if you remember the earlier case, which we have done here. We had already found out that beta is equal to under root 8 by 3. So from that we can find out V is equal to under root 8 by 3 C. Once we know the relative velocity between the frames, we know the velocities of the particles in C frame, use the velocity transformation, bring it back to laboratory frame. So we will not work it out further. I think this one can do it simply. Now let us go to a slightly more involved problem. It's not really involved, it's slightly more in the sense that instead of one initial particle, we have two particles. And things are not really in one dimension, things are gone to two dimensions. So let us read the problem. An electron of total energy 1.4 MeV. Again, when we say total energy, it means it includes the rest mass energy. Its total energy is 1.4 MeV. M is 10 to the power 6 electron volt. Collides with another electron which is at rest in L frame. So in laboratory frame of reference, there is one electron which is at rest, another electron comes and hits it, collides it, or you can get scattered, whatever you want to call it. That's not important. After the collision, the target electron, it means the electron which was originally at rest, is found to get scattered at an angle of 45 degrees, but not in the laboratory frame, but in the C frame, in the center of mass frame of reference. So the problem involves both laboratory frame and C frame. So in that sense, the problem is a little more involved. So after the collision, the target electron, which was originally the electron which was at rest, is found to get scattered at an angle of 45 degree in C frame. So from the nature of the problem itself, wording of the problem itself, it's clear that we have to be talking about C frame. Find the energy and momentum components of the target electron after the scatter in S and C, in C and L frame. So after the scattering has taken place, what are the momentum and energies of the electron in the frames? Of course, rest mass energy of the electron has been given as 0.51 MeV. So I think the problem is clear that there is one particular electron which is being hit by another electron. One electron is at rest, another electron comes and hits it. The electron which was at rest is found to move at an angle of 45 degrees in center of mass frame of reference. Okay, of course, because when you are talking of 45 degrees, it means it's no longer a one-dimensional problem. It has to be, you have to work out in two dimension, and then you have to find out what will be the energy and momentum of the particle. Probably we can work out for both the particles if necessary, or target electron in laboratory frame of reference as well as in C frame of reference. What are the issues in this thing? First of all, it's a two-particle system from the beginning, as we have said. That's no longer a one-particle system. So, like in one particle, it was very easy to find out what is the center of mass frame of reference, because you have to just go to the reference frame of reference of that particle itself, in which this particle happens to be at rest. So here it's not so obvious, but we have to work it out. The first method, which is slightly, it's a straightforward method, but little more longer method, in fact, we will give you a comparatively more straightforward method, is let's assume that C frame travels in the laboratory frame of reference with a speed v. Then find the momentum and energy of both the particles in the C frame. So, assume go to an arbitrary frame of reference which moves relative to L frame with a speed v. Then find the momentum and energy of both the particles in the C frame. Then take the sum of the momenta, put it equal to 0, because I am looking for that particular frame of reference in which the sum of momenta is 0. So, once I take the momentum of first particle and momentum of the second particle in a frame of reference which is moving with a speed v relative to L, and equate this particular momenta, sum of the momenta, to 0 and solve for v, that will be the velocity of the center of mass frame. So, this is a very straightforward standard method of finding out, even if you had n particles, that is what I will do in principle, if I want to do in a most simple fashion, that find out the moment, go to a particular frame of reference which moves with a speed v, transform all the momenta to that particular frame of reference, takes summation of the momenta, put it equal to 0. Okay. That velocity that we will obtain will be the velocity of the center of mass frame of reference. So, let us first work it out that way before we go to little more involved, little more trickier way, but simpler method. So, let us first find out the total initial energy of the electrons. As we have seen that one electron is at rest in the laboratory frame. So, I am doing this particular problem first in L frame. So, that energy is 0.151 electron MeV, and the other electron which is coming and hitting it, that has a total energy of 1.4 MeV. So, total energy in the laboratory frame is 1.91 MeV. So, this is the total energy which is available to me in the laboratory frame of reference. Let us work out momentum. Second particle is at rest, and the target particle is at rest in the laboratory frame of reference. So, obviously, its momentum is 0. Now, we have to work out the momentum of the other particle which is coming and hitting it here. Find out what is the momentum of that particular particle. I know the energy of that particle which is 1.4 MeV. I use the same standard expression, E square is equal to P square C square plus m naught square C to the power 4. M naught square C to the power 4 will be just 0.51 square, 0.51 MeV square. So, this is what I have written, 0.51 MeV square. So, this was P square C square plus m naught square C to the power 4, and this was E square, which is the total energy. So, I am solving for momentum like we did for the earlier problem. So, this becomes 1.4 square minus 0.51 square. The only thing which I have done, I have taken special units here, so that this particular thing, normally it should have been PLC, okay, but I have taken units of MeV by C. So, this value of C I need not write here. So, this is very conventional unit, traditional unit, sorry, in which we express momentum in the units of MeV by C, energy by C. So, energy we express in MeV or GeV or whatever, depending upon the type of problem, and express momentum in MeV by C or GeV by C. So, the momentum of this particular particle is if you just work it out, turns out to be 1.304 MeV by C. Of course, the momentum of the second electron is 0. That is what we have just now said. Now, transform it. Go to a frame of reference which is moving with a speed v in the L frame. I use momentum transformation. Momentum transformation is standard. Gamma, what is the original momentum? Px P1 x prime is equal to gamma Px minus Ve by C square. This is the momentum transformation equation. Momentum we have just now found out, 1.304. I am writing the unit to make it clear. Minus V is the speed, relative speed between the frames. The energy is 1.4 MeV divided by C square. For the second particle, the initial momentum is 0. So, gamma multiplied by into 0 minus V into its energy is only its rest mass energy. So, V multiplied by 0.51 MeV divided by C square. In fact, you just take the sum of these two, put it equal to 0, solve for V. That will give me immediately the velocity of the center of mass frame of reference. That is what I have written for C frame. P1 x prime plus P2 x prime is equal to 0. So, just sum these two things and work out for V. You will get V is equal to 0.683 C from this particular way of working it out. And then once you know the velocity, you can find out gamma. Once you have found out gamma, then you can transform the energy and find out what is the energy of these particles in the center of mass frame of reference, then center of mass frame of reference initial sum of momenta is anyway 0. Okay, do energy momentum conservation and you will be able to solve the problem. But as I told, there is a slightly quicker method to work it out by using the convention of the 4 vectors. So let us now adopt method 2 of working out this particular problem, going to center of mass frame of reference by using the concept of 4 vectors, as we will be seeing that though this is slightly tricky, but it is much more simpler. So this is what I said, method 2, one can use the fact that the length of 4 vector will be same in all the frames. We have discussed it earlier when we described the concept of 4 vectors, that the length of 4 vectors is what we call as a 4 scalar. Once we change the frame of reference, the individual components of the 4 vector may change, but its length is unchanged. That is a 4 scalar. So once I go from one frame, one inertial frame to another inertial frame of reference, length is going to be same. So what I can do now, calculate the length of energy momentum 4 vector in the laboratory frame of reference for the system of the particles, and I know that this particular length is going to be same in the center of mass frame of reference, and I know in the center of mass frame of reference summation of momenta will be 0. So it will have essentially only the 4th term, which is energy. If you remember, the 4 terms of the energy momentum 4 vectors were P1, P2, P3, and or rather Px, Py, Pz, and 4th term was IE upon C. So 4th term depends on energy. So let us just work it out and see how simple this particular problem becomes. So first let us write the length of the 4 vector for this summation for the system of the particle. So first 3 terms you are taking the length, so it will be A1 square plus A2 square plus A3 square plus A4 square. First 3 terms are only the momenta terms, so it essentially means the first 3 terms will give me a summation of PLI square, where L is the momenta in the laboratory frame of reference. Sum over all the particles, in this case there are only 2 particles. So what I will do, I will add the momentum of the 2 particles, and this particular term will be obtained from that. Similarly, this particular term depends on the summation of the energy of the 2 particles, because I am applying this particular, I am calculating the length of the energy momentum 4 vector for the system of the particle, for the 2 particles together, not for the individual particles. So when I am writing for the 2 particles together, this summation will be the sum of the energies of the 2 particles. First particle has the energy of 1.4 MeV, the second particle is at rest, it has only rest mass energy, which is 0.51 MeV. So summation of ELI will be only 1.91. Sum of energy of first particle plus sum of energy of first particle and the second particle. First particle having energy 1.4, second particle having energy 0.51. Similarly here, summation of the momentum, magnitude of the momentum for the first particle, which is 1.4, and for other particle is 0. So this becomes the momentum of the first particle is 1.304, for the second particle is 0, so it just becomes 1.304 square. I calculate this number, this turns out to be an imaginary number. The length of 4 vector can always be imaginary. We have discussed these problems earlier. So this will be given by 1.396 I MeV by C. Now I know if I go to any other frame of reference, this length is, for the same system of particles, is going to remain same. But if I go to a specific frame which is called center of mass frame of reference, in that summation of momentum will be 0. It means this particular term would be 0. So if I want to write in center of mass frame of reference, this term is 0 and only the energy terms will be present. Okay? So it's much easier to find out the energy in the center of mass frame of reference. Let's see how. First, let us realize that because the 2 particles that I am talking are only electrons, so what will happen in the center of mass frame of reference? One particle comes like this, another particle comes like this, both are electrons. They have to come in opposite direction because they have to make the total momentum 0, so their momentum must be in opposite direction. Now they get scattered, one of the electron goes this way, another electron goes this way. We have been told that this angle is 45 degrees. This has been given in the problem, that this angle is 45 degrees. All right. Now the only way, because initial momentum is same as the final momentum, so if this electron goes this way, making an angle of 45 degree, the other electron has to go opposite back to back, just like in the earlier case, except for the fact that it is not in the same line, but now tilted at an angle of 45 degree. But otherwise, this electron has also to go back to back, because the rest masses of the two electrons are same. It is an electron, so rest mass is same. Okay. Therefore, its energy has to be same and the moment also has to be same. So, once we realize that this is what is going to happen, then I realize that this particular energy must be same as this particular energy, as we have discussed earlier. Now, what will be the summation of the, what will be the length of the 4 vector in C frame? Summation of pi is 0. So, it means it must be minus summation of ECI square by C square. I have put the symbol C here to demonstrate that this is in the center of mass frame of reference. So, this particular thing, because the PC is 0, some of the, I am applying again, I am reminding, I am applying for the system of the particle, and for the system of the particle in center of mass frame of reference, summation P is 0. So, it contains only one term, which is this, and this must have exactly the same value as we have done earlier, because the length is going to be same in this frame for the same system of particles. So, I just evaluate this particular thing, and in principle I will get summation of ECI, and I realize, if I take under root, that this is going to be the sum of the two energies, and because energies are going to be shared equally by the two electrons, so each one of them will have an energy of 1.396 divided by 2. Let me repeat, this length of the 4 vector has only one term, which is here, which contains the summation of the energy of the two electrons. The summation of the energy of the two electron, with energy being equal for both the electrons, it means ECI is just this particular summation is just the double of the energy of the individual electrons. So, this 1.396, if I divide by 2, I will get the energy of the two electrons. So, this is what I have written. The energy of the two scattered electrons and the magnitude of the moment are same. We therefore get EC is just as 1.396 divided by 2 is equal to 0.698 MeV. So, each of the electron will have this much energy because of the symmetry involved in the center of mass frame of reference. The two particles have to go back to back, and both being the same particle with same rest mass have to have the same energy, and of course, they have to have the same momentum. I can calculate what will be the momentum of the particle by just using exactly the same relationship, and I will get that the momentum of the individual particles, individual electrons, will be 0.477 MeV by C in C frame of reference, which is center of mass frame of reference. I have found out energy and momentum. Now, in C frame, laboratory frame of reference, make a transformation. Again, you have to find out the speed of C frame with respect to L frame. Of course, if we have adopted the second method, we have so far not obtained the speed of the, in the first method we found out the speed of the center mass frame of reference, but in this particular method we have not yet found out, okay. But we can now find out, because in this particular C frame, the energy of the electron is 0.698 MeV, while its rest mass energy was 0.51 MeV. So, the gamma will be 0.698 divided by 0.51. Once I know gamma, I can calculate what will be the speed. This is what I have done. Of course, before that, let me also tell that we have to calculate the x component and the y component of the momentum, because this is now making an angle of 45 degrees, and because it's an angle of 45 degrees, so x component and y component will be just whatever is the momentum divided by root 2. Cos 45 or sin 45, both are at 1 upon under root 2. So, these are the x component and the y component of the momentum, and I must, we should be clear that we have to transform not just one momentum, we have to transform x component of momentum, y component of momentum, and also the energy of the particle to L frame. So, as I said, relative speed of C can be obtained by 0.698 divided by 0.51, which gives me the value of gamma is equal to 1.369, and I can calculate the beta as we have done using the expression gamma square minus 1 divided by gamma square, which gives me the same value which I have obtained by the first method, which is 0.683 C. I know the velocity, I know Px, I know Py, I know E in center mass frame of reference, apply transformation equations, go back to laboratory frame of reference, you will know all the energy, all the moment and laboratory frame of reference. If you are not very sure, you have done everything correctly, again apply conservation of energy and momentum in that frame, they have to be obeyed in that frame of reference if you have not made any mistake. So that is what I have said. The energy and momenta can be obtained in laboratory frame using energy momentum transformation, standard transformation. We have been using those equations earlier. One can also ascertain that the energy and momentum are also conserved in the L frame, which they have to. But that is not a part of the problem to show that, but if one wants to be very sure to see that I have done no mistake, this is the way one can do it. I just wanted to point you out one particular thing, that once we did, when described the experiment in center of mass frame of reference, the energy that we got was much less. In the laboratory frame of reference, it was 1.4 plus 0.51 MeV, while in the case of the center of mass frame of reference is 1.396 MeV. So just illustrates this particular fact that if we have to design this particular experiment, then in the center of mass frame of reference, the energy that is actually being used is only 1.396 MeV, while in the laboratory frame of reference, it's 1.91 MeV. So this is what sort of illustrates what I have been telling earlier, which I told earlier, that many times it's simple, it's energetically favorable to design the experiment in center of mass frame of reference. So you don't spend energy in accelerating or not letting the center of mass move. Now let's take one more problem in which also we are using the concept of 4 vectors and the concept of center of mass frame of reference. It's also a very simple problem, but involves many more particles. So problem is as follows, that there is a proton P which has a kinetic energy K. I mean, this problem has been given in terms of kinetic energy. Most of the time the problems are given in terms of the total energy. In this, it happens to be given in terms of kinetic energy. No issues, we know how to convert it, no problem. We also know the expression between energy, kinetic energy and the momentum. So we can use that expression here. So we have a proton which has a kinetic energy K, and this is incident on another proton which is at rest in the laboratory frame of reference. I mean, even if I would not have said L frame, we would have realized that this is not a center of mass frame of reference, because one particle is at rest, another particle is moving. So obviously the center of mass cannot be at rest. So this is obviously not a center of mass frame of reference. Now this proton, when its incident on the another proton, results into 4 different particles. After the interaction, 4 particles are found, not 2 particles unlike the earlier case. There are 4 particles which are found, 3 of which them are proton, and the 4th one is an antiproton. Just to ensure, antiproton has the same mass as the proton, same rest mass as the proton, but it has a charge which is negative to it. It has a charge which is negative. Protons are positively charged particle, while antiproton is a negatively charged particle. So you get 3 protons and 1 antiproton. Now question is little more tricky. What should be the least value of kinetic energy K? What should be the least kinetic energy that you must supply to that incident proton so that this particular reaction becomes possible? See, from 2 protons you are generating 4 particles, 3 of which are protons and 1 of them is antiproton. So obviously, if both the protons were at rest, you could not have done it, because the energy that was available to you was only 2 m naught c square, where m naught is the rest mass of the of the proton, and you are getting 4 particles, each one of which has a rest mass of m naught, as rest mass of proton. So it was not possible. Obviously, you require certain amount of energy. Now you cannot just apply conservation of energy, because the momentum also has to be conserved. But if you go back to the center of mass frame of reference, there is a certain amount of easiness, because in center of mass frame of reference I am very clear, initial momentum 0, and in that particular frame of reference, to require least amount of energy is that I can create all the 4 protons at rest. If I think in terms of center of mass frame of reference, I have 2 protons which are coming back to back like this and hitting it. They have to have equal momentum because this is center of mass frame of reference. They have the same rest mass. Now, if you are giving them too much of energy, you have 4 protons which may move anywhere else. 4 protons means 3 proton plus 1 antiproton, 4 particles. But if I want this particular thing to have the least amount of energy, I can have such a velocity such that these 4 particles are all at rest. And because all the 4 particles are at rest, then momentum is still 0. So this is what I am trying to explain. I have written in the next transparency. The least energy required would be when all the 4 particles are created at rest. But that's only possible in the C frame of reference, because it's only in that particular frame of reference that the momentum is 0. In laboratory frame, the 4 particles cannot be created at rest, because then momentum will not be conserved, because initial momentum is non-zero. It's only in C frame that the initial momentum is 0. So you can imagine that all the 4 particles are created at rest. So we go to center of mass frame of reference. The energy in C frame corresponding to the case when all 4 of them are at rest must be equal to 4 m naught c square, where m naught is the rest mass of the proton, because all the 4 particles have the same rest mass, m naught. And they are not moving because I want the least amount of energy. So the total energy which will be generated in the center of mass frame of reference has to be 4 m naught c square. Therefore, the square of the length of the 4 vector in this frame, because momentum 0, is minus e square by c square. So it must be minus 16 m naught square c square. So this will be the length of the 4 vector in the center of mass frame of reference after the reaction is over, when we have got 4 particles. What will be the length in the laboratory frame of reference before the interaction? We have momentum which is not equal to 0. I can find out what is the momentum. There is only one particle which is moving, so I can find out what will be the total momentum of that particular particle, knowing its energy. I will know the energy of the first particle, I know the energy of the second particle. I can find out the length of the 4 vector just like I did in the previous problem. Because there is only one term, so I have not written summation here. Here, of course, I have to write the totally. I have not put the summation sign to make things simple. So this p square will be given by k square by c square plus 2 m naught k. This is a standard expression relating momentum to the kinetic energy. This is what I have used earlier. The total energy of the first particle, which is coming with speed, is kinetic energy plus rest mass energy. So k plus m naught c square. There is another proton which is at rest, which has the energy of just m naught c square. So total energy is k plus 2 m naught c square. This is summation of E. I have not written summation sign here. This is the total length of the 4 vector. So the length of the 4 vector in laboratory frame of reference is minus 2 m naught k minus 4 m naught square c square. Now this length of the 4 vector after collision has to be, or after the interaction, has to be same in the length frame, in the laboratory frame of reference, and has also be the same in the center mass frame of reference. So what I do, I take the length of the 4 vector of the system of the particles before interaction in L frame and equate it to the length of the 4 vector after reaction in C frame. So this is what we am doing. I am taking before interaction the length in laboratory frame and equating it to the length of the 4 vector in after the reaction in C frame, which I know is minus 16 m naught square c to the power 4 if I want the least energy. This is what I have written. Equating the length in L before interaction to the length in C frame after interaction, I must have minus 16 m naught square c to the power m naught square c square given by this particular expression. I solve this, k turns out to be equal to 6 m naught c square. So this is the least k needed in laboratory frame. So in laboratory frame of reference, this particular particle must have a kinetic energy of at least 6 m naught c square in order that reaction becomes possible. In summary, we have discussed some problems in center of mass frame of reference and demonstrated how it becomes easy to solve these problems. And we also gave some examples of the use of 4 vector concept. Thank you.